This is 3.09, number 23. So Alex is pushing a 10 kilogram box some distance up a wall, and the coefficient of friction is given. So again, I'm going to use guide, and for the given step, I'm going to try to have a free body diagram or force diagram to help me out here. Instead of drawing the diagonal force, because I care about left and right, I'm just going to write it as the broken down version instead. It's okay to do it the other way, but it just helps me not accidentally write the force twice. So this is the push, and this is also the push given in the diagram. Other things I know, well, the mass is 10 kilograms. The coefficient that's kinetic is 0.400 unitless, and the distance that it's gone is 0.5 meters up. So that's positive if I cared about the displacement by our convention. Again, this is an incomplete free body diagram. You would need to add more to it to make sure all the terms are accounted for. So let's try doing that now using, I guess, yellow here. One thing that's not on here, they're on Earth, so there should be gravity. Gravity is pointing down, like always, and gravity is always going to be G, which we'll take to be 10 times the mass. So 100 newtons of gravity going down. Again, I could be more careful about the lengths of my arrows. But okay, 100 going down. What other forces should exist? Well, this is against a wall. So a wall is a surface. The normal force, or the surface force, sometimes it's called, always goes perpendicular out of the surface. And that makes sense because the box is moving up and down. It's not moving left and right, so the left and right forces should be balanced. In other words, there should be something that balances out this 150 newtons of force so that the box doesn't just fall directly into the wall. And that is the normal force. It's the surface pushing back. So 150 newtons is the normal force just by looking at that diagram. And like last time, for number 21, we can't just assume that the top and bottom balance because there is motion. Again, I can label it on my diagram if you want. There is motion going this way. And because there's motion going this way, there might be, it's not a constant speed, it's not saying that. So it might be the case that there is a net force in this direction. I can also see that, friction should exist. Friction opposes motion. If motion's going that way, friction should be going down. There's another friction force here. How big is that friction? I'll have to use my equation, which I didn't write down yet. The equation being friction is mu times the normal force. If I can use that, then I'll be able to see the actual magnitude. So 200 over here times the 0.4 will give you a frictional force of 60 newtons. All right, so now I have pushes, I have gravity, I have normal force, I have friction. That seems like all the forces that I should take into account here. Let me write down my unknown. The question's asking, what is the box's speed at the highest point? So V at the highest point. All right. V, I guess 2, if we want to consider it image 1 and image 2. Okay, let me write down some other tools that I haven't gotten to yet. There's E1 plus W is E2. We've kind of used that F of gravity is G times M, and we've used that friction is mu times Fn. We can also use that work is F parallel times displacement, and we can use that kinetic energy is 1/2 mv squared. So those will all be helpful. There might be some other ones that come up. To do the math, again, I think it might be easier to start with this equation, though you don't have to. E1 plus W is E2. Let me identify the types of energy at each step. So in the first picture, you can say, if you would like, that there is GPE, right? Because they are above the ground. However, I would like you to be careful about that. Remember in 3.03, we said, if you count GPE, if you use gravity as potential energy, don't count it again as doing work. And that's important because I see that force of gravity is written on my free body diagram. So it's very easy for me to look at the diagram and be like, oh, that's a force doing work because it's a force along the same axis, the y-axis, as motion. So be careful if you're thinking about counting GPE. If I'm going to use gravity as work instead, as a source of work instead of thinking of it as potential energy, it starts from rest. So there's no kinetic energy, so I would say that's 0. Again, this is one way to do the problem. I can show it a slightly different way later, but I will say that gravity is something that's doing work in this situation. Okay, so then E2 is just kinetic, because again, I'm not counting GPE because of the lesson from 3.03. Don't want to double count it. And then the work is all the different forces times the displacement. So I have the work of gravity and the work of friction and the work of the push in the y direction. So these 3 forces that I've circled. Again, we'll find that work of gravity is the same as the difference in potential energy if you had chosen to do it that way. Okay, so then using this second formula over here, I know that work of gravity is the force of gravity times the displacement. Work of friction is the force of friction times displacement. And then work of the push in the y direction only this 200 part, because it's in the same direction as motion, or the same axis as motion, times the displacement. And all those things should add up to 1/2 mv squared. If you actually plug in the numbers, so I guess -100, again, it's pointing down, so it's negative, times a +5 going up, plus -60 times 5, plus +200 times 5 equals 1/2. I guess m is 10 and v is unknown. I have an equation, I have one unknown. I should be able to solve from here. Sorry, all the distances are 0.5, not 5. My mistake. And if we add all these up, let's see, we would get 20 equals 1/2 times 10 times v squared. And if you solve for v here, you should get that v is 2. If I cared about sig figs, I could be a little more careful, but 2 meters per second. Again, a couple of things to highlight from here. One is that this work of gravity term, you can include it if you don't use potential energy. If you counted potential energy in your energy, then you'll find that you should not include this work of gravity term as well, because that would be double counting it. Yeah, so just double check that.